Okay, let's use what we've learned to try and work out what the limit is on how much fine detail shows up in a camera photograph. Now, one limit comes from the fact that our detector has pixels. So if you remember, our detector, usually a charge coupled device, is supposed to record where the light falls on it. But it doesn't record exactly where the light falls on it. Instead, it's divided up into pixels. It just tells you which pixel the light falls into. In fact, for most color images, it's more complicated. You have specific red, green, and blue pixels next door, so some sort of complicated averaging goes on. But by and large, this gives us one limit to how much detail. We can't tell whether the light falls at the top of a pixel or the bottom of a pixel. All we can tell is what pixel it fell into. So how much of a limit is that? Well, to be specific, I'm going to use my own smartphone, which is a Samsung Galaxy S6. This is a Sony IMX240 sensor, which has a focal length of a whopping 4.3 millimeters. Has to be pretty small, of course, to fit into a smartphone. And the pixels are a whopping 1.12 micrometers across. So how much of a limitation is that going to be? Well, let's go back to the optics and let's use the fact that a beam that goes straight through the middle of a lens is not deflected. So we've got L here, and we've got 1 pixel over there, so we'll call that R equals 1.12 by 10 to the minus 6 meters. And let's look at a ray of light that goes through the middle of the lens and goes to the top of the pixel, and a ray of light that goes through the middle of the lens and goes to the bottom of the pixel. What we want to know is what's the angle here between those two. Now, opposite angles are equal, so that must be the same as this angle here, theta. And so using the small angle approximation, if you remember, that L times theta equals R. So theta is just R over L, which is equal to 1.12 by 10 to the minus 6 over 4.3 millimeters. That's 0.0043, which comes out as 2.6 by 10 to the minus 4 radians. Now, radians don't mean much to most people, so let's convert that into more familiar units. We can convert it into degrees by multiplying by 180 over pi. So that comes out as 0.0149 degrees, which is still very small. We need a smaller unit. It turns out there are smaller units widely used in astronomy in particular. We have the arc minute, which is equal to 1/60th of a degree. And it turns out this is about 1 arc minute. We also have the arc second, which is much smaller than this again. Okay, so that's telling us that the fact that our detector has pixels, and they are the size, and you've got this focal length, gives us a limit to our angular resolution of about 2 by 10 to the minus 4 radians. That means light that comes in by less than that difference in angle, we won't be able to tell apart. So what does that mean in practice? Well, let's assume we're looking, I don't know, across my room. How big a size here? Oh, let's call it D. And we'll assume that's 5 meters. How big a size here could you have and not be able to split it apart at this end because all the light falls in 1 pixel? This is basically going to be a measure of how big detail can be that we can't see. Now we can use a small angle approximation again. So now D equals theta times 5 meters, which is 2.6 by 10 to the minus 4 times 5, which comes out as about 1.3 times 10 to the minus 3 meters, which is about 1.3 millimeters. So roughly speaking, you'd expect my camera to not be able to see across a room details much smaller than about a millimeter, because they'll all fall into the same pixel. That is our pixel limit in this case. Is that accurate? Well, here's a picture I took across my room of an exam paper, and indeed it looks like details of individual letters, which are about a millimeter or so in size, are blurred out. So this seems to be fairly accurate.